So welcome everybody to another session of Lógicos in Quarentena. It's a pleasure to have you all here. And on behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, I'd like to thank you very much, Professor Giovanni Sambin, who kindly accepted our invitation to give this talk. Professor, it's an honor to have you here.
It's my honor. Okay, should I start?
Yes.
Okay, I thank you and Professor Viana for this invitation. I think this pandemic experience has good aspects in the sense that we learn to keep in contact even without taking planes, and this is a good thing. Also, there is another. So I thank you and Professor Viana for this invitation. I think it's a very good idea. I accepted on the condition that it would be very informal. And in fact, it is informal. I don't show you the state of my study. I am here in this moment in my study with some books behind. You don't see the other side because it's a mess. So that's also give a sense of being informal. And it could be like you are all here in this room and we talk as you do when you talk with colleagues in your office, or even better, drinking a beer in a bar or so. So I will keep it very informal. So in this sense, I will follow this suggestion. So the topic I chose, it's always better to choose a topic in which you are interested. And in that sense, because this gives more, it becomes more authentic. It's better to speak of something that you are thinking of, so that you can convey some ideas also with the tone of voice, with presentation and so on. So when you invited me, I was thinking about, well, I have been thinking in the last 30 years about how to use, how to develop a systematic explanation of logic and mathematics using a dynamic approach, which means a completely human explanation of logic and of mathematics without any use of assumptions from above, so to say. The American philosopher Dennett calls them sky hooks. So all cranes from the ground and no sky hook from the sky. No explanation by assuming something, but everything explained from scratch. And this means, as Darwin did with nature, this means that we must follow a dynamic evolutionary explanation of things. I will have some slides after that I can show. I believe that since, as I said, since 30 years ago, I am convinced that logic and mathematics can be explained in a wholly human way. But being convinced is one thing, and showing also to other people that it is indeed so is another thing. And it is a very slow process to find step by step all good reasons, not only in theory, but since I am a mathematician mostly, there was a conversation with the late George Boulos. I don't know if you know about him, an American logician who died some years ago. We were good friends, and he said, the difference between you and me is that I am 2/3 philosopher and 1/3 mathematician. You are 2/3 mathematician and 1/3 philosopher. So since the majority in the complexity of my identity is mathematician. For me, the way to show things is to show that they work mathematically. So showing that mathematics can be done in a dynamic approach means showing that you can do it, not only by discussing it would be nice and things like that, but really do it. And mostly I have been doing developing topology since, well, I started doing topology in a constructive way in the 80s. But after finding out about this dynamic approach to foundations, I thought about using a fully dynamic approach to develop topology, constructive topology. And that is what I did since long ago. I am writing a book. By the way, to make the talk really informal, I put the picture of the Niemeyer Museum in Niteroi because it's a very fond memory I have. I was there with my wife, and my wife says that if, and she's serious, unfortunately, if you don't finish the book, I will ask for divorce. And so this should explain, should tell you how complex this enterprise is of writing a book on a completely different attitude towards foundation. Because not only, in a sense, doing the mathematics is the easy part. The less easy part is to explain why you do things in that way, and to explain that you are not assuming the standard things like existence of the universe of sets and things like that. So when you invited me, I was in the process of writing the first chapter, which explains all the foundational attitude. And there I am trying to explain, it's not easy, what I understood properly only 3-4 years ago. And that is that to be able to really give a well-founded explanation of things, one must distinguish between abstraction and idealization. I will have some slides about this, and I will say in which sense one has to distinguish them. So when you invited me, I was thinking about this, and I was thinking, oh, one thing you must know is that the first, the most important author, actually the only one who spoke about ideal mathematics, as far as I know, is Hilbert, David Hilbert. He claimed that ideal mathematics can be used in mathematics as long as it is consistent. And by the way, he claimed that not only theories like ZFC, axiomatic set theory, are supposed to be ideal because they speak about actual infinite, and not only those should be justified as ideal mathematics, but also the common law of excluded middle, which means classical logic, is ideal. And usually people are not aware of this fact. They assume excluded third is just part of logic, and logic is just part of truth. Nobody recalls, usually in discussions, that at least in Hilbert's opinion, exclude the third is not something real, but it is ideal. So starting from Hilbert and his ideal entities, I try to understand better what is these ideal entities, and so when you gave when you invited me, I was thinking about this, and I was thinking about is it really true that we can justify classical logic as an ideal entity? I'm giving for granted that consistency, Hilbert's way, is not sufficient, because we all know that classical logic is consistent. So we need something better. But perhaps it is time to start with the slides, and somehow we... Oh, by the way, all of this was to recall the talk is really informal, because it is on something I am thinking in this period. So it's not official, it's very unofficial, but I hope with some new ideas. So let's go. If I do like that. Now you see Niterói. Can you see Niterói?
Yes.
Yes.
Okay. Can I increase this window? Full screen. Okay. So that's why I gave this title, Intuitionistic Logic as Abstraction, Classical Logic as Idealization. This is my claim. My claim is that the difference between the two logics is just that one. I will try to explain what I mean, and essentially I will finish with open problems. So I call the attitude to foundations that I have been developing. I found this name dynamic constructivism some years ago, and well, 20 years ago. And since then I call it this way. I believe the best way to explain what I mean is to start from a very simple question: what is mathematics? And all, in my opinion, all is summarized by this diagram that you see, sort of a square diagram. You have reality in the bottom, then you have an arrow going up that is abstraction. I call it abstraction, and what it is forgetting some details of reality to obtain mathematical entities. Mathematical entity is what can be manipulated, what you can work with in a simpler and more effective way, because it is easier. It does not have full of details of reality, which are not essential for your purposes in that moment. But abstraction is useless unless you later have application. And this gives the dynamics, the movement between the bottom and the top line. Reality and mathematical manipulation is given by the two arrows, and that is the dynamics. If you abstract something and then manipulate it and then apply, and you get something which does not correspond to reality, that means that you have to change something or to throw it away completely. Anyway, change something. Because the aim is that when you abstract and manipulate, then you have the gain of all this is that when you apply back to reality, you obtain something which is true, which applies. By the way, truth can be seen as exactly defined by this diagram. In medieval philosophers, in Latin, truth was defined veritas est adequatio rei et intellectus. truth is the equation between things and intellect, which means truth is when my understanding corresponds to facts. So the understanding is, in this case, the mathematical manipulation on the top line. Things are reality in the bottom line. Truth is when I apply the top line to the bottom, I obtain something which corresponds, and that is truth. So in my opinion, all is reduced to this, in the very end, is reduced to this dynamic diagram. How can, from this thing, this basic thing, how can you, it's very complex, of course, to see that from this as basic, you obtain all of mathematics. It's an extremely complex development. But anyway, if you imagine to be at the beginning, when civilization started, one can check, historians tell us that every civilization, every culture has used mathematics. Some civilizations developed it by themselves. Some other used mathematics from other people. But anyway, mathematics is there since ever, so to say. And why it is so? Because it is useful. When you use that square diagram to obtain forecasts on what reality will be, that can be extremely effective. You can obtain something which you could not obtain otherwise. So, for instance, you can know how many liters of water you need to survive the crossing of a desert, which takes 2 weeks. And if you don't multiply the number of liters per day by 2 weeks, then you may make terrible mistakes. And silly example, but to show that these kind of things are really changed the way, the life of our ancestors. And in this sense, it is a sort of evolutionary advantage, and hence a continuation of natural evolution within the human species and history and culture. So if we agree on this, it's not difficult to agree on the nature of abstraction and application as an explanation of the starting of mathematics. But if we agree on this, we see a lot of consequences which are not common. One is that there is no fixed way to abstract, so there is no fixed mathematics. And there are many ways to abstract, which means many ways to do mathematics, and hence mathematics is not one. There are pluralism in mathematics is the natural thing. And the way of abstracting is simply a foundation. And this is useful for our talk today because foundation means also the choice of logic. And the choice of logic is part of understanding how you treat your entities. And so is part of understanding what you want to abstract and what you want to keep. To abstract means to forget information and keep only what you consider to be essential or relevant. There are also many levels, one has to recall, many levels of abstraction. When I give the diagram, I, of course, do not mean that everything is reduced to that. It's only a way to explain that there is dynamics. Then there are hundreds of different levels, situations, complexities. I am only just giving some ideas. A consequence of this dynamic attitude is that objectivity, universality, truth, and so on, is a result, not the origin. While usually one says, I do this because it is objective. But objective, it is exactly the opposite. Objective is when I reach something which is convincing to everybody, not we start from that. Anyway, I jump that. We must recall that application is part of mathematics, so the arrow coming from mathematics to reality. This is a dynamic evolutionary view. All experimental sciences are based on evolution, and why should mathematics be different? There are no arguments except our wishes to say that mathematics and logic should be different. After all, if you look at them from outside, they are just, mathematics and logic are just disciplines built by men. By the way, if you talk with somebody who is not a mathematician or a philosopher, or I guess also a computer scientist, if you talk with an artist, it happened to me to talk 2 days ago with an artist, exactly. And he asked me, what is your occupation? I am retired. What are you doing? I am finishing a book. What is the book about? It's about doing mathematics in a different attitude. What is the difference? The difference is that I believe that mathematics is built by humans. And he said, what's the matter? I mean, that's obvious. And so all of this to mean that it's only inside mathematicians mostly that there is this strong wish to believe that they are talking about something that is there, something that does not depend on what they do. And but this is only a wish. Very powerful. It has a very I'm not against it, but I am in favor of understanding what it is without rhetoric or without covering it with fancy speeches that do not explain what it is really. Okay, so in the very end, mathematics is just the exploration of notions and structures of our abstract thought that we built and which can be useful to understand the world. So everything is good as long as it is convincing and well-founded. The problem is that yes. The problem is, let's go to the situation of mathematics today. The common foundation of mathematics today, and since around 100 years ago, a bit over 100 years, is axiomatic set theory ZFC, Zermelo-Fraenkel with axiom of choice. Is it convincing and well-founded? How is it justified? We all know, or we should, that I say we should, we mathematicians mostly, because a lot of mathematicians do not know these matters. They give it for granted that mathematics is justified, and in particular that ZFC is justified. But what is the way to justify it? Usually Hilbert's program, namely, Hilbert distinguishes between real mathematics, which is a trustable core of mathematics. In his ideas, it is a very low-level mathematics, very concrete. He speaks several times of something that we manipulate like objects. And then there is ideal mathematics. Ideal mathematics, like ZFC, is justified by proving that the formal system namely the axiomatic theory ZFC, not the sets that it speaks about, but the theory as a linguistic apparatus. That formal system is syntactically consistent, and this proof must be done using only real mathematics. So must be done in a totally convincing theory. I call this paradigm existence as consistency, because in Hilbert's idea, and since Hilbert in most mathematicians today, the idea is that if you prove a theory to be consistent, then what it speaks about exists. I don't know your opinions about it. It's a pity that I cannot see your faces, because in this moment I would like to see the expression in your eyes. But this existence as consistency, apart from all the problems with Gödel's incompleteness theorems, that is something extra. But the idea itself that if you prove consistency, automatically what you speak of exists, was rejected by Brouwer and all constructivists. I am a constructivist, and I also believe that existence as consistency is just crazy. It's in life, there is nothing like that. It's absolutely false that if you write a novel that is not contradictory, then it will be a success. So to write a novel, it's enough that you don't kill the character at chapter 3 and then it is alive again at chapter 7 without explanation. It's not enough that you follow such consistency rules. You must write a good novel. And similarly in mathematics, to say that something exists in our thought, it's not enough that it is consistent. We must explain what it is and what is its use and what it does apply to, and so on. So the common reaction of constructivists to existence as consistency was to reject. Since they reject existence as consistency, and since in Hilbert, ideal elements are justified only by consistency, the reaction was to reject all ideal entities. In fact, if you read Arret Bishop, Foundations of Constructive Analysis, I suggest reading the first 10 pages of his book. I think you can find it online. It's out of print since ages, but I think it can be found online, or you found the second version with co-author Douglas Bridges. Anyway, the first 10 pages are fantastic read, and the main idea there is we reject ideal entities. We only want to restrict to computational content. Bishop calls it numerical meaning. And so this is the common reaction of constructivists. But the problem is, in this way, we lose a lot of nice things. We lose a powerful method. As Hilbert recalls, complex numbers, infinite series, points at infinity, all these are ideal entities. It would be very strange to refuse them because we cannot justify them in the computational sense. And in fact, no constructivist refuses the complex numbers, infinite series, and so on. So there is something to justify here. So we want to find a way to justify ideal elements in a well-founded way, and which is not existence by existence as consistency. And so we must separate ideal entities from this paradigm. And we must find a way to justify them, which is different from that. And to find how to justify ideal elements, we first have to understand better what they are. By the way of levels of abstractions, and to show you how our mind is always full with these things, I noticed while I was reading that I have written consistently instead of consistency 3 times because of cut and paste. But this is just, I'm sorry, I apologize, but this is just an example of how our mind is full with levels of abstraction. So let's see how we justify ideal entities. If you look at these examples, you easily, complex numbers, infinite series, points at infinity, you easily see what is the rationale behind them, what is the reason to introduce them. They simplify the theory about a certain topic. So take complex numbers is an excellent example. If you pass from real numbers to complex numbers, all polynomials have a 0. So the fundamental theorem of algebra holds, which simplifies the theory a lot, because you have a simple result. All polynomials have a 0. And you do not need to distinguish between a case or the other. And you just go on with the theory, which is much nicer. And the same for the other examples. Infinite series mean that all converging series determine a real number. You don't have to check what the real number is. You just accept the infinite series as long as it is convergent, for instance, by Cauchy criterion. And that simplifies matters. And infinite points at infinity, all lines have a point in common. That's much better, much simpler. 2 lines determine, the 2 points determine a line, 2 lines determine a point, and the theory is much easier. And the role, how come ZFC is ideal in this sense? Because ZFC is the theory which that treats actual infinite. Remember a bit of history. ZFC was is the result of a development beginning with the introduction of real numbers in 1872 by Cantor and Dedekind, and that yes, Cantor and Dedekind, and that was the first time in which officially infinite entities were used to define mathematical objects. Infinite entities as Dedekind cuts or Cauchy sequences used by Cantor. And then you know the story. Cantor invented set theory, starting from these considerations, and to study sets of real numbers. Then the theory became general. Then the theory had problems, the paradoxes, and then came the axiomatic theory, ZFC, essentially, at the beginning of last century, to be able to go beyond paradoxes, but still keep the power of set theory. And the power of set theory is that it treats actual infinite as an object. So the ideal entities the theory speaks of are actual infinities. And that ideal entity helps a lot to simplify the treatment of infinity in general. So the theory of infinite entities is simplified by using infinity as if it were an actual object. The problem is that if you just think for a minute to all those examples that we mentioned before in the first line, complex numbers, infinite series, points at infinity, they are all justified by the fact that they simplify the theory. They do not replace the previous theory. Imagine complex numbers that would replace real numbers. Imagine complex numbers such that you apply them to make some calculations and you find something that goes against what you would get by using only real numbers. That would be crazy. That would really be crazy. Nobody would have used such an idealization. So, and the same for infinite series, points at infinity, and everything. The typical example is the Argand-Gauss plane of complex numbers, which not only gives you an intuition of how to represent complex numbers, but most of all, it shows concretely that complex numbers are conservative over real numbers. If some of you do not remember what it means to be conservative, it's a general definition of relation between logical theories. A theory T prime is conservative over a theory T, and assuming that T is of lower level, so to say, and T prime of higher level. T prime is written in a language that extends that of T. So T prime is conservative if whenever T prime proves something in the language of T, then also T was able to prove it. So in the example of complex numbers, it is clear. Complex numbers are conservative over real numbers if whatever you prove using complex numbers about real numbers is something that you could prove using only real numbers without passing through complex numbers. So this is a technical, rigorous way to say our idealizations must simplify the matter, not go against it. They cannot contradict what we knew before. This is called conservativity. A fantastic example is, I don't know what experts think about this. I call it continuous vision. It is something I thought about by myself. And so don't take me as an expert on these matters. What is continuous vision? In this moment, each of us is looking at something, and what you see is a continuous image. In the sense, what you see, you assume to be infinitely divisible. You can, there are no pixels. You assume that everything can be measured down to the smallest unity. But this is fake. This does not exist. Not only because at the Planck scale there are quanta and things like that, but much before that. We do not need to go to 10 to minus 65. It's enough to go to 10 up to 2 or 3. No, 3. Why? Because in our eyes, the sensors are, I don't remember the name in English and also not in Italian in this moment, the name of receptors in the eye. They are around 2,000 or 3,000, like in a good monitor. So the inputs that we have from the eyes is discrete, 2,000 or 3,000, and it's not continuous. And the continuous vision is produced by our brain. It's not a perception. It's funny that we believe it is our perception, but it is not. By the way, this also explains how strong our idealizations can be. But it would be crazy to have our brain producing a continuous vision that goes against discrete vision. If our continuous vision, we understand how come, at least I imagine, how come our continuous vision is an excellent evolutionary advantage, because it allows you to keep the image fixed, even if you move your head, even if light changes, even if you close your eyes and open them again. That means to say, keep the image stable even when inputs change. And so continuity is very good to this effect. But it would be crazy if continuous vision would say, go there and get the object, and the object is not there, because the idealization contradicts what reality says. So conservativity of ideal aspects over real aspects is part of the game. It's something we cannot abandon. So all in all, we can summarize our understanding of abstraction and idealization in this way. Abstraction is to forget some information to simplify manipulation of objects in the top line in the diagram. And it is justified by application. By applying abstract notions, we must get something that applies to reality. Idealization, note that one thing is to forget, to disregard. Another thing is to add some properties. You add to idealize means to add some properties or entities to simplify the theory. And it is justified by conservativity. So quite different from consistency. So it's a pity. Let me see. Can we go out of this? It's a pity that we could not see each other. But anyway, I go on. Are there any questions up to now? Bruno?
People are already asked for questions, but I'm not sure if they are going to make it now or in the end.
Okay,
if someone has any question by now.
If you wish. I just was realizing that I have been talking by myself for a long time. So, reaction.
Does anyone has any question by now?
Oh, okay. So let's go.
People are saying they don't want to interrupt. So let's keep it to.
Okay. So we only have 5 minutes because essentially my talk is some open problems. So at this point, once if we accept that this distinction between abstraction and idealization, and this characterization of them by application in one case and by conservativity over real aspects in the other case, the next question is, how can we justify? Hilbert says that the law of excluded middle, namely A or not A is true, whatever is the proposition A, can be justified as ideal. But he means that then it is justified by consistency. There are very short proofs of consistency, not only of propositional logic, but even of predicate logic, classical, I mean. I remember of one proof of 3-4 lines, essentially. by trivializing every quantification and every proposition. So it's very easy to prove that classical logic is consistent. But if we look at it as ideal, can we justify it as by conservativity and not just by consistency? And if so, over what do we show that it is conservative? And what is the reality it tries to simplify? So my claim is that what I say in the title of this talk. Intuitionistic logic can be seen as a result of abstraction, classical logic as a result of idealization. So I agree with Hilbert that classical logic is ideal, more than intuitionistic logic. Why do I say so? Because we start from a concrete level. A is a proof of proposition A, which sometimes is written as A is an element of A in the Martin-Lev tradition. A is a proof term showing that a proof term that is a derivation of the proposition A, and it is written as membership because it follows the same rules as types. Anyway,
Professor?
Pardon?
We have a question.
See? Yes?
Valeria?
Hi, Giovanni. How are you doing?
You are the Valeria I know?
Yes, that's right. Hello, can you see me?
Bye.
It's a very nice talk. We're kind of having a great time with all this kind of very interesting and deep thinking about mathematics. But I was going to ask you, kind of, did you kind of consider, are you going to consider in the next minutes that you have anything about the recent proposals by Pravitz and others, including Luis Carlos Pereira, Elaine Pimentel, and myself, to do ecumenical systems that put together at the same time classical logic and intuitionistic logic?
No, I'm not aware. It's a good suggestion. I'm not aware of that.
I'll send you later on then the paper by Pravitz that started.
I would please send me also your paper. I would appreciate that a lot.
Sure.
As you see, I am very much interested in these matters.
Yeah, no, and it is very much about this business of how you define. I mean, it is interesting. Maybe we can kind of make an approximation of your ideas of conservativity and the ways we are thinking about. I mean, I think we are agreeing that a conservativity is one of the main criteria, but of course, proof theory are other criteria. So I'll send you that.
Very good. Yes, that is very interesting. Oh, by the way, your question allows me to say, as I say, it is, you're right. I believe what is new is the whole setup, the whole framework. Technically, I'm not saying anything new. This is the last slide. Yes. And as you see, it's very poor. It only contains some future work, so to say, some open problems or some lines of research. So it will be very interesting to see if you have already developed some pieces of this.
Of course, that's not poor. It's just kind of interesting and open-ended. That's what you mean.
Yes.
Thank you.
So, other questions? Otherwise, I just finish the last 2 points. So we have the concrete level. A is a proof of a proposition capital A. And then this is a standard. You abstract from the proof term little a. That is, you identify all proof terms. So what matters remains only if there is one or not. And one obtains the judgment A is true. Namely, if you identify all proofs, what matters is only if there is one or not. which means if there is a proof, it means A is true. If there is not, it means A is not true. And so you can see the judgment A true as obtained from abstraction, by abstraction from a more concrete level. And by the way, I forgot to write here. It's very interesting that intuitionistic logic is conservative in this sense. I hope you understand me also, even if I speak only with words and with no symbols, because I forgot to write that. So intuitionistic logic, in the sense of judgments, proposition A is true, is conservative over the more concrete level, judgments of the form small a is a proof of big A. This is a theorem in proof theory, which says if you have a proof in intuitionistic logic of some formula A, then by some meta-mathematical arguments, you can, you have a program, you have a procedure, which allows you to go back to the concrete level and find a proof term which shows that indeed it was correct to say that A is true. So you have exactly what you have in the diagram, in the square diagram. You have the level, the concrete level I call here, A is a proof of a proposition. You abstract from the proof term, the small a, you obtain judgments A true, you work with those, you obtain a proof, then you apply it to show that you indeed had a proof term of what you obtain as true in the abstract sense. So in that sense, not only you have that intuitionistic logic is obtained by abstraction, but also in the case of intuitionistic logic, you can show that it is conservative or better, that it is really abstract because you can apply it again to reality. Classical logic is in an idealization. I mean, I think that is clear already, because when you say that A or not A is true for every proposition, even if we have no clues about the proof A, that is clearly an idealization that does not come by abstraction from anything. It is just to simplify the matter of truth of a proposition. But the matter is, are we now able to justify this by conservativity over something? Over intuitionistic, can we justify classical logic as an idealization that is conservative over intuitionistic logic? I doubt. I doubt very much, because there are many results that say that either it should be the opposite in some sense. The Gödel-Gensen interpretation tells you that intuitionistic logic is stronger than classical logic, so it can interpret classical logic. So anyway, that's my impression, that it cannot be shown to be conservative, but it is an open question. So I would stop here. There was a full second part that I jumped completely. That was, I just show you the title, if I find it. Yes. The second part was just a repetition from this talk in Rio 7 years ago, because to justify, I don't show you the slides, but I only tell how come this talk is relevant for the talk of today. In this talk, I show that, let me see, yes. I show that all logical constants can be defined by a scheme like this. I show you an example. Better disjunction. or implication. So the top line is it's hard to, oh yes, no. The top line here is the definitional equation of implication. And my claim is that, actually I prove that every logical constant is obtained as a solution of a definitional equation of that kind. So all implication, disjunction, conjunction, but also for linear logic, times, and par, and so on. They are all obtained by solving a definitional equation, and the solution has always this shape. One direction is formation from right to left in the equation, and the opposite direction has one is the top line, but you find it an explicit rule as the bottom line in this scheme. Anyway, you can show that all logical constants are defined and obtained in the same way. And the main point is in all possible logics. This follows exactly what the late friend and colleague Kosta Došen stressed for a long time, namely that what matters in a logic is not the rules of logical constants, because they're always equal for all logics, but structural rules. And this topic of the definitional equations to justify logical constants is further evidence that Kosta Došen was right. And why is it relevant here? Because only how come we talk about concrete or abstract or ideal when we speak about logic? Because we are thinking of the notion of proposition. And how can we restrict to the notion of proposition and do not care about logical constants? Because of what I just said. Because what matters is only structural rules. And structural rules is just a way to determine our notion of proposition. For instance, if you have weakening and contraction, then it means that your notion of proposition is abstract. It's not resource dependent, and so on. If you have classical structural rules of weakening at the right of a sequent, that means that you have the classical notion of proposition. And so in that sense, one can restrict consideration of these judgments, what is a proposition and what it means it to be true. And that's why I restricted to those without considering logical constants. My voice is disappearing, so it's a good reason to stop here.
Thank you very much, Professor, for this amazing talk. So now we have some time for questions. If I would, as usual, I would like just ask people to manifestate first in the chat to avoid a lot of people talking at the same time. I'm not sure you are seeing the chat,
I see
but
very quick.
A lot of people are agreeing you.
I've seen that
Professor.
Professor.
Yes, you may write it.
Thank you for invitation. For the invitation. Another question by Valeria. Why not?
Yes, Valeria may speak. While Ray.
Well, there is someone in the chat wanting to ask a question in the chat, Bruno. So kind of.
Yes, while he's typing, maybe you can do your question.
Sure. Giovanni, the other thing that I wanted to discuss with you is the business of categorical interpretations, categorical semantics of classical logic. We all know that, I mean, I just want to hear your personal view. Sorry, I've forgotten to turn my camera on so that you can see my face when I'm gesticulating and trying to explain.
Oh, yes. Now I see you. Very good. Hi.
So, hello, how are you? So the question is, do you have a personal view on which one of the models of categorical classical logic is better? And if so, why and why not? I know it's not very related to what we're talking about here, but
the matter is not relation, because I like everything related to logic. But the matter is that you are mentioning two topics that are not in my heart, so to say. I do not have nice feelings both with categories and with classical logic. So putting the two together is even. I mean, I do not feel good in these matters. I'm not against, but I do not feel they are consonant to my understandings, and so I have nothing to say about your question.
Okay, no, fair enough. I just thought I was going to check if there was anything that I mean, I agree with you. I'm much more in favor of intuitionistic logic myself too. But on the other hand, I feel that we have to pay attention to what the other guys are saying, and there is so many more guys who want to do classical logic that I feel we have to try to find ways of accommodating them. And I was thinking that maybe you had a personal, less bad version of classical logic, if I may say so.
Oh, yes, I understand what you mean. No, perhaps I am more radical than you. I believe that it is 100. Brouwer said so, I think, 100 years ago. That and it is incredible that the situation is even worse than 100 years ago. He said that logic, only classical logic, without realizing the revolution of intuitionistic logic, is like making classical physics even after relativity theory. And I still believe so. I really believe that classical logic is a mistake, not because it is contradictory, but because it does not talk about reality in a faithful way. And by the way, what I'm doing today is trying to understand better this claim. How come intuitionistic logic is more faithful? I believe it is, but how can we explain this? Can we give some measures of the fact that classical logic is not trustable?
I see. Thank you. That's good. That's good. That's good. Thank you.
Ray, we are waiting for the question.
Sorry.
So, Inti, do you have a question? Your microphone's muted. Okay.
Is it my turn?
Yes.
Yes, I can hear you.
Okay. First of all, thank you for such an exciting talk. My question concerns the relationship you established between mathematics and reality. Of course, I'm not thinking of the most obvious problems that one as a philosopher might find with a claim as yours, but I'm thinking of something a bit more humble. I'm sure, my question is a bit more humble.
Oh, humble. Okay.
It is not a great question, but a humble one.
Okay.
As I'm sure you know, using only classical logic and the mathematics that stems from it, you can build real numbers, and which captures a sense of continuum. But if you do it with intuitionistic logic, you get a different kind of real set, which captures a different sense of continuum.
Yes.
So if these two senses of continuum are to be found in nature, can how can we make sense of the unity of reality? And if the intuitionistic continuum is real, because as you said, intuitionistic logic is correct, how can we make sense of the empirical success of classical analysis?
Before answering, I must ask Bruno, can I be politically incorrect?
Sure.
Okay. It's like speaking about capitalism or free market economy. With free market economy, we had a lot of nice things, a lot of production, money, success, health, cars, and so on. But this does not mean that it's all good. This does not prevent me from criticizing it radically. It is destroying the planet, social injustice, and so on. So very similar is with mathematics. Classical mathematics has a lot of success, but this does not mean it is correct. In my opinion, much better can be done. So coming to your specific question, if there is nothing wrong if we have one idea of real numbers given by a constructive approach and one idea of real numbers given by a non-constructive approach. This is exactly the topic of my book on topology. What exactly the main topic? What it means to have topology in a constructive sense. And one can see that there are many more interesting insights doing things constructively than doing things classically. For instance, a typical example of something that you discover is that it is very important to use the point-free approach to topology, because if you do things in a point-free way, you can maximize effectivity. Point-free topology is effective. I can speak only by slogans in this moment. It would take a long time to explain. But point-free topology is effective, is part of real mathematics. And real numbers are obtained as ideal points over a certain point-free topology. But it is an idealization that I can control, because I start from something effective that I do not throw away. I keep it there, and I see how to build ideal elements, namely ideal points, over something effective. So not only it is quite possible to have different approaches, but also, in my opinion, the constructive one can give much deeper insights.
Thank you.
Thank you for the question.
Ray Gill is asking in the chat, how do we know that the law of excluded middle isn't obtained by some way of abstraction? What is the difference between len and, say, the axiom of choice, which makes the first one ideal and the other not?
The difference between lemma, law of excluded middle, and axiom of choice?
Mm-hmm. Yes.
I never spoke of axiom of choice. I spoke of ZFC. ZFC is ideal because it is a theory with no interpretation. It is just a linguistic nonsense, which could be consistent, but we don't know, by the way, by Gödel's theorem. Anyway, even if it is consistent, it is just talking. In that sense, it is ideal, as ideal is the law of excluded middle, because even there, I talk about the truth, even if I don't know what it is. I talk about the truth of A or not A, even without knowing which one is true. So it's a very funny understanding of disjunction. In fact, the matter is complicated by the fact that intuitionistically, one can say that the disjunction, the classic disjunction, does not exist. The classical logic does not have this junction. They have a negation of the negated. So A or B does not exist. What exists is not A and not B, according to an intuitionistic perspective. But I don't know if I answered. Perhaps if he can.
He's saying after that, yeah, it's an example of some statement which presumably isn't ideal. Pick one, please.
Presently is not ideal. What does that mean?
It's in the chat. I don't know. He was talking during when you were speaking. I don't know which exactly part of your talk, what of your answer was. Is he talking about? Ray, if you want, you may clarify, please.
Is there a place where I can read the question?
Yes, on the top right, there is a button with some kind of balloon with 3 lines. It's the chat.
Okay. And it is where?
On the top right.
Yes, I found it. And the question is...
is in the end of the chat. By Ray Gill.
Ray Gill. Yeah, it's an example of some statement which isn't ideal.
He says he was talking about the axiom of choice.
Which is not ideal is everything concrete. 2 plus 3 equal 5. That's not ideal. That's abstract. Because it abstracts from, if I take whatever 2 things and whatever 3 things, I put them together, that if I count them, that is 5. So it is abstract, but not ideal. Ideal means I add something which is not in reality. It's not always so clearly distinct. For instance, natural numbers are both abstract and ideal. The abstract part is 2, 3, 7. The ideal part is it is infinite. Why is it ideal? Because there is no infinite. Infinite is only in our mind. Infinite is only, I can go on adding 1 with no bound. That's somehow ideal. But it is acceptable. And in fact, the intuitionists accept this kind of infinite because it is conservative. Accepting that natural numbers are infinite does not destroy finite natural numbers. Does not say, if I assume the capital N natural numbers are infinite, I don't obtain that 2 plus 3 is 5.5 or 7. I still obtain that 2 plus 3 is 5. So adding the assumption that you have an infinite set does not destroy what you had before. While this is not true with ZFC. You destroy the notion of measure, you destroy the notion of existence, you destroy a lot of things that you had before.
Luis Carlos?
Are you listening to me, Giovanni?
Yes. Oh,
nice seeing you. Nice seeing you again. Hello. Great talk. Thank you very much for the talk.
Thank you for the invitation.
No. Just to start with a small remark, just to check if you agree with me, that if you are a classical mathematician of faith, if you really believe in classical mathematics, somehow you collapse, right, these 2 levels, the level of abstraction and the level of idealization. He does not consider just idealization. I mean, he really sees the idealization as the abstraction. There is no separation from this.
I agree. Idealization becomes stronger than abstraction. Exactly. And they believe when the 2 clash one with the other, idealization is stronger, and so abstraction goes away.
Yes, and it is somehow it's a consequence of the principle of existence by consistence, right?
Yes.
Because
Yes.
existence by consistence collapse these two levels. I think you're completely right in this sense. But I have a small curiosity. You mentioned the double negation translations of Gödel Gensen, and in the very first page of Gensen's paper from 1933, Gensen talks about the difference between Heiting's arithmetic and Peano's arithmetic as being an external difference. And I think he thinks that he could have a mathematical structure, right? And you could put intuitionistic logic below it and produce Heiting arithmetic. Or you could put classical logic behind it and produce Peano's arithmetic, right? So you change the logic and you change the mathematics in this sense. But the mathematical structure would be independent, so to say, from the logic in this sense, because the logic would be external. In fact, I don't really agree with that. And a technical result that shows that this is wrong is that if you take, for example, the logic of constant domains, which is an intermediate logic, it will collapse into Peano's arithmetic. It will not produce a kind of intermediate arithmetic. But I think that from a constructive point of view, right, this idea that you can separate the mathematical structure from the logic wouldn't fit really from the constructive point of view. I think that in the process of abstraction, the way you will produce your mathematical manipulations at the abstract level, it goes together with the logic. There is,
in fact, you are stealing what I thought to be an intelligent answer. You are just saying what I would have answered, that it is difficult to separate logic from the rest, because you use logic when you abstract, when you create your entities.
Yes.
And so in the same moment that you adopt classical logic, you will see things through classical logic. There are hundreds of examples, well, not hundreds, but dozens of examples of mathematical entities that when you look at them constructively, you see that there are many more than what the classical mathematicians did see before. Because if you look at things with the classical eyes, it's like looking with glasses with yellow lenses. And so you do not see the distinction between white and yellow. And classically, you do not see the distinctions between exists and not for all not. And for instance, it is really incredible. One of the reasons for writing the book, causing my divorce, perhaps, is that I introduced 25 years ago a symbol to express the fact that two subsets, A and B, have some point in common. And I use a symbol of this kind, showing that the two subsets have some point in common. And it is incredible how much you can do simply by using that notion that classically does not exist. Because classically, it is exactly the same as A intersected B, different from empty set.
Okay.
While intuitionistically, it is totally different. And introducing that and using that all the time makes you see a lot of things that otherwise you would not see. So I totally agree that the logic is somehow built in our minds when we define things. So it's very difficult to separate.
Okay, thank you, Giovanni. Thank you for the talk.
It was nice to see you.
Nice to see you.
Hi, Professor Sambin. It was very nice to hear you after quite some time.
Yes, I remember.
Yeah, I met you in Japan.
Where are you now?
Where
are you now?
I'm in Delhi now, India.
Okay. Mm-hmm.
Yeah. So first, if I remember correctly, you had spoken about minimalist foundations in Japan. So
Yes.
is this connected to that program?
Yes, Minimalist Foundation is the formal system expressing what I call dynamic constructivism. Dynamic, I am very careful to keep the distinction between, so to say, the philosophical attitude that I call dynamic constructivism and a formal system that expresses it. And this formal system I call Minimalist Foundation. I am in favor of keeping two different names exactly to recall that one thing is our attitude, what we think in our mind, and one thing is the formal system by which we express it. Well, usually with set theory, they confuse the two levels.
I have two more questions. I hope I'm not taking up too
You
much
ask
time.
Bruno if you are allowed to.
No problem.
Okay. My second question is, it starts with a comment, really. I really liked your comment that classical logic was a mistake. But I have this confusion that when we do, even when we are doing constructive mathematics, sometimes we have to apply classical logic from the outside for doing some of the proofs. So my understanding is you can push classical logic as far as you can, but at some meta level you have to bring it in. Is that?
It is just false. This is not true.
This is not true. Okay.
I never use classical. I am a constructivist simply because my mind, thanks God or thanks evolution or thanks my parents, I don't know why, my mind is set up in a constructive way. I never do classical, only classical arguments by contradiction, double negation, exclude the third. I never use them, not because I follow a discipline, but because they are not natural to my mind. So I'm pretty sure that I never use classical logic in the meta language.
Okay.
And so in my opinion, you can do without.
Okay. And my last question is regarding the axiom of choice. So if I'm not mistaken, the axiom of choice is not accepted, the full axiom of choice is not accepted by intuitionists.
That's a very delicate topic. So the axiom, people say that we have discussed about the axiom of choice more than on all other foundational topics in the history of mankind. Anyway, the first remark to say about the axiom of choice is that its meaning and its strength depends on where, in which theory you consider it. If you consider the axiom of choice in type theory, it is provable.
Yeah,
if you consider it in Zermelo-Fraenkel set theory, it is an extremely powerful, 2,000 or even more, 2,000 different equivalent manifestations of axiom of choice. And that is because you have power set axiom and excluded middle. Together with axiom of choice, that is like producing an explosive with two ingredients that by themselves are not terrible. But when you put them together, it explodes. That's my feeling.
So intuitionistic type theory is the only place where you can have the axiom of the full axiom of choice. Is that right?
More or less, yes. Yes. I don't know about other predicative. I don't remember in this moment if you have it in Myhill, Axel, Constructive ZF. Could be. Could be that it is not typical of type theory. But in type theory, it is very natural because it comes just by the justification of sigma, that is the expression of existential quantifier. So it's built-in, so to say. You don't have to prove it. It's built-in the explanation of logic.
Thank you.
So, and as I know it's a bit late for Professor Giovanni, the last question from Diogo.
I am amusing myself now with questions, much more than before during the talk. So I can go on as you wish.
Hi, Professor. Thank you for your talk. I have a quick question. You said that the justification for accepting complex numbers is that it is a conservative extension of the other kinds of numbers. And my question is that even though it is a conservative extension, it says something about new identities, or I mean, new entities, like the complex number. So what justified these new assertions about this new entity?
So I thought, yes, you're right. It's what I said, it's not clear. If you look at the history of mathematics, complex numbers were called imaginary. They were invented here in Italy, mostly, perhaps not only, but mostly, by people who were trying to solve polynomial equations. And they understood that if they added some numbers such that you pass into the square, you would get -1. Then you would have solutions of all equations of degree 2, and this would simplify the theory. So this was clear in Renaissance. People like Scipione del Ferro or Cardano, other people, other crazy Italians of that period already knew about this possibility. They call them imaginary numbers. So I am not contrary to some constructivist people. I had a very strict education, but I try not to be moralist. I try to be realist. But realist means realist in the sense accept things, do not judge by moral arguments. So I'm not against using some ideas to simplify your treatment of a certain theory. That's an excellent idea. If we imagine I, such that I to the square is equal -1. In this way, all equations of degree 2 have 2 solutions. That's fantastic because it simplifies calculations a lot. You go on and realize that it works, that you save a lot of time. And all this is very good because equations are very important, because it's not just a play, it's not just playing around, it has effects, real effects. So finding a new method is a good thing. Now, the point is, how do we justify it? The problem is not inventing new things, introducing new things. The problem is how we justify them. My claim is we justify if they do what they are expected to do, namely simplify the picture. They cannot overtake all the rest. Otherwise, there is no point in introducing them. What is the point of introducing things if I don't care about whether they destroy all the rest or not? That would be stupid. And in fact, it is stupid, in my opinion.
Okay, thank you, Professor.
Did I answer?
Yeah.
Okay, good. By the way, they changed the name from imaginary numbers to complex numbers when they realized that they are conservative, which took 2 centuries. The Argand-Gauss plane is end of 18th century, so around 2 centuries after the introduction of imaginary numbers.
That's interesting to know. Thank you.
Yes.
So thank you very much again, Professor Giovanni. It was really an amazing talk, and thank you very much for accepting our invitation.
Thank you. As I told you, I'm very glad, first of all, because I could speak to people who, judging from questions, have been listening, and that that is always nice. But also because I like Brazil, I like people there, and so it's also nice to keep contact.
Thank you very much.